Okay, so we were talking about the particle model of atoms and states of matter. Well, the particle model of matter, actually not atoms. And we talked about solids, get my highlighter, and right how their structure and their volume and their shape is determined by the particles that make them up and their energy. So solids have particles that are close together. They have the attractive and repulsive forces between neighboring particles in balance. How does that matter? Well, because the electrostatic forces exert both an attraction and repulsion. The attraction keeping helps to keep the particles close together and in a regular pattern. The repulsion resists compression, and also the particles are in continuous motion. So in the case of solids, they are vibrating about their fixed positions. They're not moving about in space because they're all close and packed together. So that's written over here. And then I went on to explain about the expansion and contraction of metals when the weather gets hot and when it gets cool, and how in construction uh, that needs to be a consideration for architects and engineers, leaving space for solids to expand and contract, because if you don't, you're going to come across problems. And that's actually one reason why you end up noticing cracks in buildings over time, because the constant expand well, one reason, right? And so because the constant expansion and contraction of the cement and concrete and whatever else the material is, eventually it gives way. At some point, because the contraction, expansion over the number of years, how quickly it happens depends on the quality of the material. So how good the particles of the material are, if you're talking about it in physics. And so eventually, they break from somewhere in between, and that's how cracks appear. Coming to liquids, so the particles are slightly further apart because they've gained energy, and so the forces of attraction have become weaker. Right? They have more energy. They're moving past each other, and they're moving rapidly over short distances. Uh, so there's two types of movements happening over here. One is the vibration of individual particles. The other is their movement in space. As I mentioned, the force of attraction become weaker. They're not strong enough for the liquid to maintain a regular pattern or regular structure. They do have a definite volume, so they're occupying a fixed three-dimensional space. Evaporation occurs, that's particles at the surface gaining enough energy to overcome the attractions and then leaving the surface of the liquid. And because of the energy they've gained, the distance is greater, and so not only are the forces of attraction weaker, but the repulsion is technically weaker as well. They move further apart, so not far apart, and so that makes liquids compressible, not a whole lot, but definitely more than solids. Evaporation versus boiling. So evaporation happens only on the surface of a liquid or something that's wet. So obviously liquids are involved in talking about wetness. Boiling happens throughout the liquid, and evaporation can occur at temperatures lower than the boiling point. All right. Then today we will talk about gases and how the particle model relates to that. So the particles and gases are much further apart. Let me just put in a heading. Aram, you have a question?
Yeah, like what's the difference between evaporation and boiling?
So evaporation happens only at the surface of a liquid. It's just like particles at the surface that are gaining energy to leave the liquid body, and so there is a loss of particles taking water as an example, uh, right? So water molecules from the surface of the liquid are leaving that. Eventually, over time, depending on how quickly evaporation is happening, will lead to a reduction in the volume of the liquid body, because particles are being lost, meaning mass and matter is being lost. Boiling is a point where a change of state is happening throughout the entire liquid, right? And that only happens when they've reached, so below boiling, when you see, for example, it's if you're boiling liquid in a pan or a pot or any container, and somewhere around 60-65 degrees maybe, you see steam rising, right? And so heat rises, energy is traveling through the water, and the particles at the top have the most energy, and so some of them start escaping the liquid, and so the water is not boiling at that point, right? It's just happening at the surface. When it comes to 100 degrees
Okay.
centigrade, so at 100 degrees centigrade, water boils. That is the boiling part, and that is when there's a change of state happening for the entire body of that water. Okay, and so all the particles are gaining energy and turning into steam or water vapor, right? So that's the gaseous form of water, and the temperature in that case will stay at 100 degrees centigrade until a complete change of state for the entire body of water has not occurred. Does that help?
Yeah. So does that mean boiling is an example of physical change?
Oh yeah, definitely. The state of matter, the state is changing, so definitely.
Thanks.
Okay. So gases, their particles are much further apart, as we know, and right, compared to solids or liquids, about 10 times further apart. Right now, we are talking about a molecular scale, so that would be probably in nanometers or micrometers, but still, right, 10 times is, compared to solids and liquids, there's a lot. About 10 times. Uh, they are much less dense, and they do not have, right, any particular shape. So no particular shape, and also no particular volume. Right, so the shape thing we understand, right? The particles further apart, so there's no attraction. Uh, like the force of attraction gases are even weaker, much weaker than in liquids, and so there's nothing holding them in a specific position, so no shape. And for that same reason, right, they don't even have a fixed volume because they're so far apart, and they're moving about, that they can occupy whatever container. Right? So you've got a small container, right? You fill a gas in, it's going to take up the whole thing, right? You put that same volume of gas, so to speak, or that same amount of gas in a larger container, and it will take up the entire volume of that container. And so, what's the volume of the gas? It depends on the volume of the container.
Okay.
They have, right? They're much less dense, and we understand that why, because density is mass over volume. So the mass is not changing, right? Because mass is the amount of matter in a substance. So the mass is the same. The volume, however, right? Now, obviously, to calculate density, you need certain parameters to be kept constant, right? So temperature and pressure, and you take a fixed volume and then you get the density of a gas. But right, generally they take up more space, and that is why they are much less dense. They are much more compressible. And again, that is because of the distance between them. So I'm just scribbling spot. Get this out of the way. And so, right, that huge distance between them means that the forces of repulsion are also not as effective for keeping the molecules in a particular at a particular distance. And so a gas can be compressed into smaller containers. And in fact, that is what is used in, for example, aerosols or right, LPG or CNG, if you heard of these, liquid petroleum gas or compressed natural gas. And these are basically gases under high pressure. And so what actually happens is, because they're put in a container under high pressure, right, the gas molecules are compressed and come close enough to actually become liquid, right? But they are not liquid in the sense that by a change of state that they've lost energy. They're only in sort of a liquid form because they are under high pressure. So when you use an aerosol, for example, when you shake it, you feel like there's a liquid inside. But when you press it, you have a gas coming out, right? Or in that case, you got a liquid that's aerosolized, so that's a bit different. But the gas, like in right, Sobia, you're in Sharjah, right? So you got those gas cylinders,
Yeah.
right?
Yeah.
So when you turn on the stove and you light a matchstick and so the gas, it's obviously gas, but inside the cylinder under high pressure, it's sort of liquid.
Not that I have seen, but yeah.
Well, I wouldn't recommend you try and opening the cylinder, but
But yeah, yeah. Yeah.
okay. The particles are moving around at a very high speed. And they mention that air at 0 degrees centigrade is actually moving at 500 meters per second, the particles. Not that you feel that, but that's how fast they're moving, even when the air is still. And we're talking about 0 degrees centigrade, so not some place that you would want to be without proper clothing. Obviously, it's cold. You would think that the particles have lost sufficient energy, but no, they're still moving up pretty fast.
Okay.
Okay, and so right, collisions, right, and that is something that will be right mentioned again. So there are collisions between particles. As far as solids are concerned, they're in a fixed place, so nothing's colliding. Liquids collide more frequently because they are further apart as compared to solids, but still close enough. In gases, right, the collisions are infrequent. So because they're so far apart, there's nothing dictating uh, whether or not they will come into close proximity, close enough to the particle and then actually hit it. Right? If they're in a container, then obviously, let me clarify this with other particles. Right, but in a container, then the gas particles are obviously hitting the walls of the container. Now, anything special about properties? So they're moving at high speeds. They are moving at high speeds over large distances. So compared to water, which was moving over short distances, these guys are moving over large distances. And right, there's less interaction between individual particles. They have no shape or volume. Determined by the container, compressed. Yeah. So that's all about gases. Any questions?
No.
No.
Okay.
No.
Next, so now that we've discussed the particle model, we're going to talk about temperature and kinetic energy, which is something that we know already, we have mentioned. Right, basically, when you raise the temperature, particles gain energy and they vibrate faster, and right, they move up. Not only do they vibrate faster on their own, but they also move about in space depending on the state that they're in. So even in solids, when energy is supplied, right, they vibrate because obviously they're not moving about in space, they're in fixed position, but in their fixed positions they're vibrating, right, so that vibration increases, they vibrate more strongly. And so we've talked about kinetic energy, that's basically the energy of a moving object, and so these vibrating molecules also have kinetic energy. And so when energy is supplied, when they are heated, when their vibration increases, their kinetic energy also increases, and so the average kinetic energy overall goes up. On the flip, when temperature is reduced, right, energy is lost, obviously, and so right, vibrations are slower, and the average kinetic energy is also less. Achha, is there a point where particles lose all their energy and they stop vibrating? So we talked about 0 degrees Celsius, and right, air particles, the air still moving pretty fast. So how much energy would you, and right, we're talking about energy, so basically you're talking about temperature, right? That's what we're talking about. And so at what temperature would the particles lose all their energy? So that
Zero.
is, yeah, go ahead.
Wouldn't that be 0 degrees?
0 degrees Celsius? No, because air particles are moving pretty fast, and that means they have kinetic energy.
So when are they not moving?
Exactly. So, right, when right the temperature at which right particles lose all their kinetic energy, right, is what is called absolute zero. Why is it called absolute zero? Because it is on a different scale, temperature scale. In terms of right over here, we sort of go into the Kelvin scale. Short, brief topic that comes at the end of the unit 2.1. Right, but since we're mentioning absolute zero over here, what happens is, right, as we saw, if you plot a graph and you have temperature on the x-axis in degrees centigrade, and you've got energy on the y-axis, right, in joules, kinetic energy. What you see is at 0 degrees centigrade, the kinetic energy of particles is not zero. And so, right, at 0 degrees centigrade, you still have, the particles still have energy. So if we extrapolate means that because this is linear, It's a straight line. So what we can do is we can take the graph linearly in reverse and see, oh, at what temperature would there be zero energy? And so that's somewhere over here. And that would come up to minus 273 degrees centigrade. Now, right, this value, this temperature is called absolute zero. Why is it called absolute zero? Well, one reason why, because there's zero energy at this temperature, and secondly, on a
There is no heat.
huh?
There is no heat as well, right? At
Heat,
zero.
heat, heat being relative, right? So let's say energy,
Okay.
right? I mean, you would say that there is no heat at 0 degrees centigrade. So again, right, heat in terms of like energy at minus 273 degrees centigrade, talking about kinetic energy. And so the particles, right, in this particular chapter, in this context, in the context of thermal physics and the particle model, right? So at minus 273 degrees centigrade, the particles would have zero energy. That means they will not be vibrating. So there's no vibrations. Forget movement, right? They're not even vibrating. So there's zero kinetic energy. And the other reason why it's called absolute zero is because there's an alternative temperature scale that is put to use in physics, and that is the Kelvin scale, right? So minus 273 degrees Celsius is on a Kelvin scale 0 degrees Kelvin. So right, Kelvin or Kelvin, right, is given by the right symbol K, a capital K. Right, it's not lowercase k because lowercase k is used for constant values in
Yes.
different equations. Right, so we're not using lowercase; it's a capital K. Right, and so right, because minus 273 degrees centigrade is 0 degrees Kelvin, and that is right. In fact, they don't even add the degree sign here. So there's 0k. This is not okay. This is 0. Right, and that is absolute zero. So it's 0 on the absolute temperature scale, which is the Kelvin scale. Right, and this brings us to certain questions that you would get where you'd be asked to convert between degrees centigrade and degrees Kelvin. Right, and because 0 degrees Kelvin is minus 273, that would mean 0 degrees centigrade equals to 273 degrees Kelvin. It seems like it's very hot, 273, but on the Kelvin scale, it's just 0 degrees centigrade. Right, so for us, it's still cool. Now, when doing equations, right, or whatever question you're given for conversion, right, the Kelvin scale is represented by the letter T, right? That is not for the temperature, but the Kelvin scale overall. Right, so the Kelvin scale is represented by the letter T, and the degrees centigrade is represented by the Greek letter theta. And so a formula for conversion between Kelvin and degree centigrade is the Kelvin scale is 273 plus theta. And so if they're giving you something is, for example, right, it's at 80 degrees centigrade. And converting that to Kelvin. Right, so T equals to 273 plus 80, which will give us how much? 353, I believe.
Yeah, 353.
All right, so 353 Kelvin. And if you go the other way around, you want to convert 100 Kelvin to degrees centigrade. And so again, E equals to 273 plus theta. So theta equals to 273 minus T. That's 273 minus 100, which gives you 173
173.
degrees centigrade, which is hot.
Yeah.
Okay?
Okay.
Well, actually, no, I did that wrong. Go back. You didn't even spot that.
Spot what?
That would be
Oh, the
T
plus.
minus 273, not 273 minus T. So that would
Yeah.
be 100 minus 273, which will give you minus 173, which is cold. Very cold. Okay.
Yeah.
Okay. And so yes, that little diversion is part of the syllabus, right? And minus 273 degrees centigrade is absolute zero at which temperature, right? Acha, theoretically, absolute zero is a theoretical concept, so to speak. In labs, in experiments, they've gotten very close to absolute zero, but not quite there. Because technically, you would say, well, if you actually reach a point where you lose all the kinetic energy, then, things will stop working. But that's just, my very layman sort of explanation to you guys, right? Obviously, scientists are trying to achieve that, but they've gotten very close to it, right? Not there yet, but so any questions about this? Anyone?
No.
Like, but why? Isn't it easy to have like itna cold environment?
No, because you actually have to pump all the energy out.
Oh,
And so, where are you going to put all that energy? And that's also, you're talking about energy on an atomic level.
yeah,
It's not like you're going to Murray in the winter enjoying the snow. It's cold and you're keeping yourself warm with a jacket. It's not like that,
yeah.
right? So it's not that easy. Anything else?
No.
No.
Okay.
Even in the Antarctica, it's not absolute zero.
Oh no, not at all. I mean, if it were absolute zero in Antarctica, then how would you have wildlife? Well, not well, yeah, Antarctica has fish at least, right? So Arctic and Antarctic, you've got wildlife, you've got whales and other guys. You would say, well, they're insulated, they've got fat, but right, if you're losing all of your energy, then that insulation wouldn't do a lot of good, right? It would greatly affect you. So yeah, and not even there, right? But absolute zero is not found anywhere on Earth. It is only, again, it is a theoretical value. They've gotten close to it under experimental conditions only, not in any natural condition. In fact, even liquid nitrogen is not that cold. Right? If I just quickly search up the temperature of liquid nitrogen, just give me a sec. Come on. 190 minus 196 degrees centigrade, right? So that would make it about 77 Kelvin. So yeah, still not zero. It's pretty far off from zero still. Achha, one thing to just point out that the difference in each temperature degree is the same for both, right? So a 1 degree change, so that's right, a 1 degree difference in centigrade and Kelvin is the same. So if you're going from 100 degrees centigrade to 101 degrees centigrade, and so on the Kelvin scale, that would be what now? 373 degrees, sorry, 373 degrees Kelvin to 374 Kelvin, if I'm doing this correctly. Yeah. So that increment is the same. Just keep that in mind. All right.
Okay.
Next up, we have pressure and kinetic energy. And so when we're talking about pressure, we're talking about gases. So, right, gases exert pressure and they have pressure. Why do they have pressure? Because when gases are in a container, right, they have kinetic energy and they are moving randomly and they are colliding with the walls of the container they're in. And that is the main player over here. Right, so depending on how much kinetic energy they have, right, that is the speed and therefore the force. So, right, they are hitting the walls of the container with a certain force. Right, and we know that pressure is force upon area, right, and so when they're hitting the walls of the container with a certain force, they are exerting pressure, right, and because, right, we're talking about average kinetic energy of the gas particles. So at a certain temperature, right, the force that they are exerting, right, would be even. It would be the same, and that would lead to, right, a certain value of pressure. Right, so it's not that, oh well, this particle is exerting this pressure, that particle is exerting a different pressure. That's not how. So you take the average and you take it overall. Okay, now what happens when you increase the temperature? Right, the particles gain energy, so they've got more kinetic energy. That means more collisions. And if the volume is the same, so you're not getting a larger container, you have the same container, right? That means that they're going to be hitting the wall with greater force. And when they're hitting the wall with greater force, the pressure inside the container, the pressure of the gas, is going to go up. Make sense?
Yeah.
And not only are they going to, have, right, more force, the collisions are also, right, so the number of collisions, they're more frequent. So more collisions, more frequent collisions, right. What's also happening is, right, there's a change of momentum for the gas particles. So at each collision, with the wall of the container, right, the gas particle undergoes a change of momentum. and that change of momentum is actually what is producing the force on the surface of the container, or the wall of the container.
I have a question.
Mhm.
Since the temperature is going up, right? Like the temperature is increasing. So does that it does change the matter, right? Like the state of matter, right?
You can't go beyond gas now.
Okay.
If it were happening to a liquid, if you were boiling a liquid in a sealed container, then, right, if a change of state is happening and the liquid has expanded and there's gas getting trapped over here because the liquid is boiling, well, for one thing, if the lid is shut, right, you would actually end up superheating it, so that's a different thing. But also the pressure will go up and you would actually end up having a problem that the container might explode. You've heard of pressure cookers,
Yeah.
right? So you can superheat them in a container, so the food cooks much more quickly in a pressure cooker. So there are a number of things involved. You've increased the pressure inside the container, right? It's heating more quickly, and right, it is pressurized. Like, the point is, it's pressurized, and you're heating it. So you need to be very careful when you are, you need to depressurize a pressure cooker first, depending on what type it is, right? And so you need to let all the steam come out that has collected inside the container. If you don't do that, if you just, remove the lid without, letting the steam get out, or if the lid wasn't properly sealed, or anything else, right? And you
It will burst.
it and it happens, right? Now, that bursting thing can also happen with gases, right? So if you heat it enough in a fixed container, right, the gas is expanding, right? And it doesn't have enough space. So up till a point, right, the pressure increase, how much the container can bear depends on the thickness of the container and the material of the container, XYZ, right? But there will come a point where it becomes critical and there's a danger that it might actually blow up, right? Even if it's made of metal, right? So at each collision, where was I? There's a change of momentum for the gas particle, and that change of momentum produces a force on the container, uh, oops, on the container wall or surface, right? And if you just go back and recall the chapter of momentum and impulse and all of that, we know that momentum and force and all of those are interlinked.
Okay.
Okay. All right. Now there is a very brief topic of Brownian motion, which is part of the IGCSE syllabus. It is given in the O level book. It's not part of the syllabus, it's given as going further. So I'll cover that and then we'll move on. I'm not covering any of the practicals at the moment, right? Once we're done with the main content, I'll go back and cover the practicals. They're easy. So Brownian motion is basically, without filter. So as you can guess, it's named after a scientist. There's a question. Yes, Haram? Haram, do you have a question? Okay. Right. You can put it in the chat or you can ask me later. Right. I think your mic's not working, I guess. So Brownian motion is basically, right, when you observe fine particles in air, right, and the random movement. Now, to make this simple, have you ever observed in any room, whether it's your house, a room in your house, or anywhere else, or maybe out in the open, have you seen dust particles in sunlight?
Yes.
Sobia, have you seen
Yeah.
this? Yeah. So if you've observed the dust particle is like, going here and then there and then there and then there,
Yeah. Yeah.
right? That's how it's moving. That is basically Brownian motion, right? Why is it happening? Because dust particles are much bigger than the particles of air, the molecules that are in air. And we know air is like composed of oxygen and nitrogen and carbon dioxide and all of that. But air in general, right? So it's much larger. Dust particle much larger than air. Okay. Now what's happening? You've got the dust particle over here, and you've got the air molecule over here, the particles in the air, and these guys are moving about pretty fast. As we know, it's a gas, and it collides, and so right, it pushes the dust particle here, right? The dust particle is now here, and some other guy comes in, right? An air molecule hits it over here, right? Goes in that direction, and that is why you see dust particles moving. Or otherwise, it's dust particles are solids. So, right, this also gives us a good explanation and an example of, right, the kinetic energy of molecules,
Okay.
right? Air molecules are moving, we're hitting the dust particles, right? We're causing the dust particles move in a particular direction. Another particle comes in, hits that, causes the direction to change, move in a different direction, and that's basically what Brownian motion is. All right.
Yeah.
Okay. Next up, do we have time? We have time. Oh,
Yeah. 14
we
minutes left.
yeah, we are now going to talk about gases and the absolute scale of temperature. So what do we have? We're going to talk about pressures of a gas, effect of pressure on change in effect on pressure on a change in temperature. Um, okay, I think we can minus the practicals. I think we can cover this right now, hopefully. Okay, so now we are actually on 2.1.3 in your textbooks, and we are going to study the relationship. That's not the heading given in the book. We're going to study the relationships between temperature, pressure, and volume of gases. So first off, to start off by talking about the atmosphere, right? And they talk about atmospheric pressure. And so air is matter, matter has mass. And so in the atmosphere, I mean, you've got air from ground level up till, up. And right, so they mention that the weight of the air around us, right, in a room is about 500 newtons. Right? We know it about weight as a force. So what would its mass be if it's 500 newtons of weight? Anyone? Oh, come on.
What?
What would the mass of this air be if it has a weight of 500 newtons?
Sir Haram says 51.
9.8 is the gravitational field strength. We multiply it by that.
So we no, actually divide 500 by 9.8. Alright, so that is the acceleration due to gravity, which is 9.8 meter per second square. This is what we don't know. This is 500. And so 500 divided by 9.8 is going to give you, right, rounding it off to two significant figures, you're getting 51 kgs of air on you. Of course, you don't feel that because it's spread out, but the overall feeling that you have when you again, I wouldn't say we feel that because we're born into it, and so our bodies are adapted to it. We might feel that difference when we go to a higher altitude where there's lower pressure, there's lesser air, so we might feel it then, or we go into a vacuum container, right, a vacuum chamber, sorry, not a container, so there's no air in there, so we might feel the difference then. Yeah, so basically, right, this air around us, air has weight. How is it? And because of its weight, air exerts around 100 kilopascals of pressure. So we know, right, pressure is in pascals, and it is force upon area, so that is, right, Newton per meter squared. And air, the pressure air exerts is 100 kilopascals, right, or 100,000, right, Newton meter squared of pressure. Or you can just write it as 10 to the power 5 in standard form.
Yeah, okay.
That's a lot, right?
Yeah.
Okay, now when you have a container, for example, a can, right, and it is filled with something, whatever this is filled with, unless it's a solid, right, because in solids we're not talking about pressures. So if it's a liquid, most likely if it's a gas, right, and so that substance is exerting pressures on the walls of the container, and then the atmosphere is exerting a pressure from the outside on that container, and only if the pressure inside the container is equal or greater than the atmospheric pressure, will the container be, it will hold its shape. If it is less, right, the atmospheric pressure will crush it. Now, why don't we see this happening around us? Because even if we have like an empty container, it's filled with air, right? So that would give us the equal pressure. So there's pressure of air inside, there's pressure of air outside, right? And so obviously the container getting crushed. If somehow you are able to suck all the air out and create a vacuum inside the container, and the vacuum means no air, right? And so it's empty on the inside, right? There's air on the outside, and your container, whether it's a plastic bottle, or a soda can or whatever will get crushed. Now I do have a video for this. Unfortunately, it's not one where they're creating a vacuum. It is slightly different, but the concept is the same. Right, so it's a short, and so let's take you there. Hopefully, I won't have any copyright issues with this one.
That's what I was about to point it out.
I will okay, put that on the recording as well. Okay, this one. Right, so I'll just tell you what they're doing is that they're heating the container to allow all whatever's inside to leave the container. That's reducing the pressure. It's a soda can in this case. And right, and so the pressure is getting lower, and then usually what they do is that they put it inside a beaker of water, and so the pressure of the water on the can is higher than inside the can, and you will see that the can is immediately crushed.
Low pressure inside the can and high atmospheric pressure outside the can. The atmospheric pressure is going to try to push and equalize those two different pressures, but it'll have to push on the water that's in the beaker and try to push the water into the can. Since water can't flow that quickly into the can to equalize those pressures, we're going to see the can actually get crushed under the pressure just from the atmosphere, the pressure that you and I live under every single day. 3, 2, 1. Low pressure.
How was that?
Interesting.
Right, now the explanation this guy gives, obviously, right, so it's not just the water, right? The can is empty, they've heated the gas out of it, the liquid, and so when he's inverting it and putting it into the beaker of water, right, the atmosphere is pushing down on the water in the beaker as well, and so that will push the water into the soda can. But as he mentions that the water entering the soda can is not fast enough, and so a low pressure inside the can and the, right, will not be filled up with water quickly, and so the atmospheric pressure is high enough to actually cause the can to collapse.
Okay.
Okay, let me go back. Oh, we're out of time. I didn't. Yeah, I guess I was having fun. So I think I'll stop here for the day, and we can continue. So unfortunately, I wasn't able to complete it, but we can continue this the next time, and then carry on. In fact, I will continue this next class and I'll also go over the practicals.
Yeah. Okay.
Any questions, anyone? Any comments, opinions, anything you'd like to share now? Otherwise,
No.
hold your peace until next class, or you can just put in a message on WhatsApp, whichever you prefer. All right, I'll upload the class. You have the link, so you can access it now. Right? Do you need the slides? I'll share the slides.
Yeah.
Yeah.
Okay. All right. See you guys next time.
Okay.
Okay, Office.
Allah.
I got this.